Great. Now the difficult part is done. So hi, everybody. Thank you for joining. Now at this point, this is the point when I introduce the speaker. Given I'm the speaker, well, that would be a bit awkward. So I will just say, hey, I'm Federico Tomassetti, in case we didn't meet before. And I founded Strumenta, where I work as a language architect. Just a title I came up with, but given I created the company, I can call myself whatever I want, I guess. And today we are going to talk about building an interpreter in Python using Pylasu. And Pylasu is one of the open source libraries we created. And we are going to cover this topic because, well, in the last few years, a lot of clients have asked us to have a language engineering solution that they could use from Python. So I didn't expect that, but we adapted to reality and learned something. And so I should start with a disclaimer. I'm not really a Python expert. So the biggest project I wrote in Python was a word generator called Word Engine. I mean, I wasn't the only author of this tool, but basically was a tool to simulate some phenomenon like plate tectonics movements, erosion, and so on, just with the goal of generating some sort of realistic word map. So totally unrelated to language engineering, but before we started working on Pylasu, that was the biggest project I wrote in Python. So if I say something stupid regarding Python, please let me know and let's see if we can correct that. So before diving in code, let's spend a few minutes doing a recap of what StarLasu can do and maybe adding a few more concepts to what my colleague Lorenzo presented last time. So the basic idea is that we recreated the same library 4 times in 4 different languages. All these 4 libraries are open source, available under the Apache license 2. And yeah, basically we started creating the first one in Kotlin. It was called Pylasu for Kotlin language support. And then when we needed to create the equivalent in TypeScript, we call it Pylasu, in Python Pylasu, and 10 days ago or so, we released also SharpLasu for C#. You may wonder how we came up with the design of Pylasu, and I wish I could tell you that we spend a lot of time thinking of the perfect design. We talk with some researcher, and then, I don't know, we interview some wise monks in Tibet. But in reality, we just started writing a bunch of utilities every time that we realized that we were missing some feature for our daily work. So in this way, we built originally Pylasu. Then at some point, we stopped and we did a refactoring. And then basically we copied most of the design in the different libraries, adapting them depending on the capabilities of the language and trying to make, to adopt the idioms that are typical of the different languages. For example, in Pylasu, we use a lot of reflection, but reflection is not available in TypeScript. So my colleague Alessio came up with some brilliant ideas to find alternative solutions that are specific to Pylasu. So in this sense, not every library is exactly the same, but we try to adapt them to the specific language. And these libraries are something we use to build language engineering pipelines. And this is an example of a pipeline. For example, this is a pipeline that we could use when we want to implement a transpiler. The idea is that at the beginning or the end of the pipeline, we could have something different from an abstract syntax tree. For example, in the case of a transpiler, we have some code as input and some code as output. Let's say that we are writing a transpiler from COBOL to Java. The input will be a bunch of COBOL files, and the output will be Java files. But beside the input and the output of the whole pipelines, every other step receive and produce an abstract syntax tree. So we can combine these blocks because all of them can work with abstract syntax trees. In the case of a transpiler, for example, we start from the original code, we parse it and get an initial abstract syntax tree. Then we refine it by resolving symbol, calculating types, and doing other stuff. Then we transform it in the abstract syntax tree of the target language, for example, Java, and then we generate code out of it, and we end up with some Java files. But we can have pipelines for other goals. For example, if we are implementing an advanced editor with features that we can call collectively language intelligence, for example, showing errors, performing autocompletion and stuff like that, then in that case, we also benefit from an abstract syntax tree because, for example, we analyze the abstract syntax tree to identify errors that we show in the editor. Or we use the abstract syntax tree to figure out which identifiers can be referred to in a certain point in the code, and this is useful to implement things like autocompletion. Or if you want to build an interpreter, like we are going to do later today, we also have a pipeline. We still parse code, resolve symbols, and calculate types, and then we have the proper interpretation parts that will navigate the abstract syntax tree and do something based on the content of the abstract syntax tree. Now, you may have noticed that in these different pipelines, there were some blocks that were reused most of the time. We typically call these two blocks, we combine these two blocks in what we consider a parser. So for example, if we want to parse RPG, we recognize the original code and then we do things like symbol resolution and calculating types. And these blocks can be reused in an editor, can be reused in an interpreter, can be reused in a transpiler. So the design of StarLasu allows us also to reuse blocks like parsers, but also code generators. So blocks that allow us to define an abstract syntax tree programmatically, for example, as part of a transformation in the context of a transpiler, and then generate code out of it. So if we need to build a transpiler, we typically can just reuse a parser and a code generator and just write the wiring if you want. So transforming the RPG abstract syntax tree into the Java abstract syntax tree, but before and after that, we can just reuse components. And this is a terrible video, and I'm just... okay, let's skip this part. I'm just trying to show a very basic UI demonstrating a transpiler. This UI, I can upload an RPG file, then a second step of the pipeline, an abstract syntax tree for the RPG code is written, then the corresponding abstract syntax tree for Java is derived through a transformation, and finally, this abstract syntax tree will be used to generate a Java file. So I wanted just to show some graphical representation of the different stages of one of these pipelines, in particular the pipeline that we use for transpilers. One characteristic of StarLasu is the fact that we can combine different blocks written in different languages. Now, this is an example that is a bit, not very realistic. Typically, we do not just write components in 4 different languages for the sake of it. But what typically happens is that some of our clients want to write some part of the pipelines in their favorite language, while perhaps we want to reuse an existing parser that we've written, let's say, in Kotlin, so using Pylasu. And maybe they want to write the transformations themselves in Python because they want to evolve them over time, so they want to own this transformation. And the design of StarLasu allows us to support this use case. And in this way, we can avoid basically rewriting parser all the time in the favorite language of the client. And how do we achieve this support for multiple languages in StarLasu? Well, basically, we define an abstract syntax tree in some language, let's say in Kotlin. Then we analyze the Kotlin classes and we derive a meta model. From this meta model, we can generate the abstract syntax tree classes in the target language. And then we also want to serialize instances of our abstract syntax trees. So we just serialize them in JSON and we unserialize it on the other end. In practice, this is what happens, that we may write a parser in Kotlin. So we just write some data classes. Then we have some code that goes over the Kotlin code and obtain a meta model. So some sort of representation of the information present in the data classes. And this meta model is used as input to generate the corresponding Python classes. What happens at runtime is that when we run the parser written in Kotlin, at some point we can call the JSON serialization module, that is just a feature of Pylasu. We get a JSON file, and then we use a JSON unserializer, for example, from Python. This JSON unserializer is generated also from the meta model, and you can imagine a piece of code that say, oh, okay, I have a JSON object. If the type is, I don't know, entity, then instantiate the class, the data class entity in Python, and then populate all the fields from JSON fields. And so the Python stage can call the Kotlin stage, get a JSON back, unserialize it, and do his own thing in Python. One may wonder why we are not using EMF instead of recreating our own thing. And well, I guess one could have different opinions on that, but from my point of view, EMF is a little bit too complicated. At least when I dive first in EMF, I found it very difficult to learn all the mechanics on EMF. And one may comment that eventually StarLasu will get as complicated of EMF. Perhaps we will see, but at least we can get rid of any dependency on Eclipse and OSGI. And also another important thing for us is that we can imagine this platform from the beginning with the intent of supporting multiple languages, while EMF was created for Java specifically. I know there are some ports to other languages, and we have also tried using them a little bit. Some are more mature than others, but I think that EMF was really not designed from the very beginning to support multiple languages. Then, as I said, different people can have different opinions about that, and it would be also interesting to hear what you think about that. So what we are trying to build today is an interpreter, so no surprise there. And let's see if these things work. Oh, this thing seems to have thrown an error. Well, let's see if it works anyway. This simple interpreter, well, is based on two different languages. One that I can use to configure this application and decide what kind of entities I will be able to create. In this case, I can create a project, and the project has a name as a client, and a client has a name and an address. And these things, this list of entities and the definition of the different fields that this entity have comes from a language we created for this demo. But then we have also a small scripting language that we can use, for example, to create a project and to do things like setting the name of the project. My wonderful project. Let's see. Okay, nothing is happening. Maybe is this other thing? No, something decided to crash because probably I've done some change at the very last time. That was not a good idea. Okay, so perhaps later when we look in the test, we will fix it, and this will make the presentation more interesting because, you know, it's always so boring when all the demo goes flawless without any test failing. So yeah, we could do that. Well, or maybe we can also undo this refinement that I did the last time, and probably weren't the most brilliant idea. So maybe we can also try that and see if this works better. No, probably then is something I change in the configuration file. Maybe the fact that I'm missing these. Let's see. Maybe here I do not see errors anymore, but this part is still not working. Okay, so we will get it solved later. Now, before going back to the demo, I want to just explain very shortly how we structure parser. And I want to specify that we use Antler for the first two stages of the parser, so the lexer and the first stage parser, or the parser generated by Antler. But then we do not use directly the parse tree produced by Antler, but we instead convert it in an abstract syntax tree that is implemented with Pylasu. We do that for two reasons. The first one is for simplicity. Now I will not try to give a proper definition of the difference between a parse tree and an abstract syntax tree. First of all, because I don't know the proper definition for that, but I want just to say that in our case, the abstract syntax tree is a simplification of the parse tree. So we throw away details that are irrelevant for us. And the second thing is that the abstract syntax tree is implemented using our libraries, and they provide all sorts of features that we need to do our job. So we take advantage of that. So going back to the demo and to fix the demo, let's see. Maybe I can first explain how we write the abstract syntax tree, and then run some tests and probably fixing them for the remaining time. So how we define the classes of our abstract syntax tree is simple by using data classes and by extending node, which is our base class defined in Pylasu. Then we have a list of fields. For example, we say that a script is just a list of statements, where statement is another kind of node. As is typical in any scripting language, we have statements and expressions. So in this case, these are abstract classes. As far as I know, in Python, there is not an abstract keyword. So I just wrote in a comment that they are abstract. But in case I'm wrong, please let me know. I will just add the abstract keyword. Then we have some other, the classes for the different statements. For example, we have print statement that extends statement, which extend node. And we say that the print statement has a message, which is just an expression. Create statement is a node which give us the opportunity to introduce something a little bit different. So a create statement could be written like this, like create project, for example, to instantiate an entity named project. And it can optionally also introduce a name that I can use to refer to the instance that I just created. So this particular field entity is not just a string, but is a reference by name. Now, while parsing, I will just encounter project as an idea, as a string. But in my abstract syntax tree, I want to write down that this is not just a simple string, but this is a string that I use to find something else. So this is a reference by name. So when I will initially build the abstract syntax tree, I will just write down that this reference by name as the value project as a string. But later on, during the symbol resolution step, I will navigate the abstract syntax tree, find out to which definition of entity this is connected, and then update my entity, my reference by name, to write down a link to that particular entity, so that I will be able to access it more conveniently and do things as we will see in the rest of the presentation, if and only if we will be able to fix the test. Another field is instead the name, which is just of type string. And so this is a field that represents a primitive value. In our context, anything that is not a node or a list of nodes or not a reference is something that is primitive, because it has not a particular meaning in the abstract syntax tree. So this is how we define the classes of our abstract syntax tree, which is pretty simple. But then how do we instantiate those classes? Well, we instantiate those classes by converting the parse tree that we obtain from Antler. And the way we do that is by defining these two AST methods. Now, in this presentation, I've taken for granted some knowledge about Antler, but just to say a few words for people that are not familiar with it, the idea is that with Antler, you define a grammar, like, for example, this one. So you say, I don't know, a script is basically a list of statements. A statement can be one of these three alternatives can be, for example, the create statement with the keyword create, an entity, which is just an ID, and optionally the name of the instance that I've just created. Now, based on this grammar, Antler will generate a parser, and this parser will also contain different classes to contain the different constructs of my language. So that here, for example, I have inside this file a bunch of classes, like, for example, this one. This set statement context class has been created to contain an instance of set statement, and set statement is specified here. So for each of these constructs, we get a class to be generated by Antler. Now, what we want to do is basically to add a method to that class. However, we don't want to modify the generated code, so we use some metaprogramming black magic to modify outside of the class definition, the definition of the class, and just add a method. And the black magic is this extension method. And hopefully you don't see this, this panel with the commands from Zoom, so you can actually read what is written in the IDE. But basically, here we just add, open the definition of the class and add the method. In this method, what we do is, okay, I see a question in the chat. Ed is asking, in the grammar, it looks like the syntax for set is set name of p to something. Had noticed maybe my error, because here before I wrote as instead of to, and so maybe that was the error. This is one error. Probably there is more than one. But something seems to me more, okay, at least now create project works. So this is probably something here. I don't know if maybe was that literal needs to be written in the other way. So yes. So thank you, Ed, for fixing, well, identifying at least one of issues, one of the issues that we have in the code. If you're lucky, there will be many more. So we will have a lot of fun fixing them, but yeah, good. Good. So in this abstract syntax tree method, what we say is take a node from the parse tree and convert it into the equivalent for the abstract syntax tree. A lot of these methods are very boring because we just convert them one-to-one. So in this case, for example, we convert the parse tree node representing the whole script into the abstract syntax tree node representing the whole script. And in this case, we don't do any simplification really. So this is a conversion one by one. We also look into the children of my parse tree node, so the statements, and we convert them one by one into statement in my abstract syntax tree node. So a lot of these conversions are extremely boring. However, there are a few things that we may want to do that are a bit more creative. For example, when we have names that represent references, we do not just treat them as string, but we instantiate a reference by name, like this is the case here. We also do other simplification, like, for example, we throw away parentheses. Now, parentheses are useful during parsing because they influence the order in which we recognize certain operation, and so they influence the order of execution. But once we have built the parse tree taking in account the parentheses, at that point we don't need them anymore. So we can throw them away in the abstract syntax tree. So in the abstract syntax tree, when converting parentheses from the parse tree to the abstract syntax tree, we just throw away the parentheses and we convert the content of the parentheses. So this is one difference between the parse tree and the abstract syntax tree in our case. Another thing that we do is that we get rid of all the simplification, all the performance optimization or other weird things that we needed to do in the grammar and that were reflected in the parse tree. For example, one thing we notice is this, that when writing an Untitled grammar, it seems to me, and perhaps someone will correct me, it seems to me from our test that the parser can be, in some cases, significantly faster if I group together the binary expression with the same level of precedence. So instead of having one rule for division and one for multiplication, I have just one for division and multiplication in the same place. So this is what I've done here and here. The problem with this is that I end up with one node. And Mike is commenting that this is also the only way to give them exactly the same level of precedence. This is also an added bonus. But the problem that I have with this is that I get a node that represents both division or multiplication. So doesn't represent something that makes sense conceptually. It's just a result of a performance optimization. So in the conversion from the parse tree to the abstract syntax tree, I take advantage of this conversion to get rid of that. And I actually create different nodes for division and multiplication. So when I get an instance of division or multiplication expression contest, I end up with a cleaner division or multiplication. So I do this cleaning here. So let's see some tests. This test seems to pass, how boring. But let's just see an example of a test that we can write using Pylasu. In this case, we have an example of script. And as Ed noticed, here I use to and not as. Small but important difference. And this is a simple script where you see I can create things, I can assign fields, and then I can print something and concatenate strings. Okay. What I want to do is parse this thing and then verify that I get the abstract syntax tree that I expect. In this case, I can just define the abstract syntax tree that I expect programmatically by instantiating the classes of my abstract syntax tree, so the data classes that I've defined before. More in detail, what I do is I verify if the result of my parser is a result that contains 0 issues and the abstract syntax tree that looks like the one that I expect. We can also maybe dive here in the parser, in the parse method to see how it works. For some reason, it didn't navigate to that. So, well, it's not a problem. We'll just go there. In our parse method, what we do is simply this. We invoke the Untitled Lexer. we just change the error listener, because the default error listener will print some error in the console while we want to collect all the issues. But beside that, we just invoke the normal lexer from Antler. We also invoke the normal parser from Antler. And then we invoke the 2AST method that convert the parse tree to the abstract syntax tree on the root of our parse tree. Then this 2AST method will invoke recursively the 2AST methods on all the children. Finally, for now, we have to assign parents explicitly. Basically, because of the way in which we build the abstract syntax tree, each parent knows its children because they are just the values of its fields. But the opposite is not true because the children do not know their parents. So we navigate the whole tree once we have built it, and we assign set parent so that at that point we are able to find the parent of a tree, and if necessary, to navigate from any node to the root of the tree. Beside that, our author tests are not super exciting. We check that our parser is able to identify errors and return issues. We show some features of the abstract syntax tree, like the possibility of navigate through children, stuff like that. But given we are a bit short on time, I will just move forward. Anyway, this repository is available online, and I will share the link later on during the presentation. So a quick recap, we define the classes of our abstract syntax tree with simple data classes. We then define this 2AST method to specify how to convert each kind of node in the parse tree to a corresponding node in the abstract syntax tree. And then most of the tests we typically end up writing when we test the parsers are tests of this kind, which we specify in the abstract syntax tree programmatically, and then we verify that our parser produced the abstract syntax tree that we expect. So a lot of boring tests. And now I think we can dive more into the interpreter part. Yes, we could execute code in different ways, transpiler, compilers, interpreters. This time we are going into interpreters. This is an example of a script, and this is an example of a script that is correct, not like the one that I tried to write on my own. And now to see the interpreter, I think the most practical way is just to run some tests. Now, our interpreter we require to get a list of entities that we can use in our language. You remember that here, for example, I could use projects and clients, and project has certain fields and clients other fields. So our interpreter needs to know a list of entities that can be used, so that I can run create project, but I cannot make run, I don't know, create book, because there is no entity called book. So in this case, I define my entities programmatically. I could obtain this entity by parsing entities file like this one, but instead I write them programmatically. This is the part of the evening where I start coughing until the end of the presentation, so good. Here, Here I want to test a simple script where I create some instance of client, for example. So what I do is I instantiate my interpreter with a list of entities that we've seen before. I expect the interpreter at the beginning to have no entities of any kind. Then I run a script. In this case, I could have parsed the script, but I decided just to write it programmatically. And then I run the script and I expect to have one entity of type client. And my entity should have, thank you, Marco. My entity should have, the instance of my entity should have the ID 1 and the values unspecified for name and address. Now, let's dive into this and see how our interpreter works. Our interpreter, first of all, resolves all the references. And this is the moment in which we go through our reference by names and we find to what they refer to. In our case, we have a create statement. A create statement as a reference by name to the entity that is being used. So for example, if I have a create project at the beginning is just a name, but I want to find the definition of the entity project. So the relevant point is this. And in this case, you see I have the create statements in the variable s. It has entity that is a reference by name. It contains the name client, but refer at this point as no value. So how do I resolve it? Well, I look for something with the name client among the entities. So this is why I need the list of entities to now do this mapping. So I do the mapping and I can see that the reference now is changed and contains actually a link to the entity that I've defined elsewhere so that I can, for example, figure out that it has two features. I was able to resolve the entity, so I don't need to show any issue to the user. Then I guess there is no other things that I need to resolve. For now, check types is not relevant. And the symbol table initially is empty. We will see that create statements can populate the symbol table and other some expression can refer to the symbol table, but so far, in this case, we don't need it. What we do here is moving to execute each statement one by one. We have a create statement. In this create statement, we check that we were able to resolve the entity, because if not, we cannot really instantiate our entity. Given we can, we just call a method of our interpreter that will create an object, will check the definition of the entity, and will be easy because I will now pass the definition of the entity, given I take it from my reference by name, and so the interpreter knows already the list of features that are specified the entity, and so it can initialize correctly this object. In this case, I using create statement without specifying the name, so I don't need to populate the symbol table, but if I specify the name, I will just add this instance in my symbol table. So I can basically go back and I can complete my test and it succeeds. Now, I think we have time to see this other test and then dive into questions. In this other test, we have a create statement in this case, we also assign a name to the instance we are creating, and then we use statement. And in this case, instead of writing the script, we are, again, defining the abstract syntax tree just programmatically, which is also a way to avoid all the syntax errors like we had earlier in the demo. Now, if I run this script now, in my resolve script, let's see what we encounter. We encounter the create statement, and it works like before. But we also encounter a reference expression. Now, let me go back to the test. You see that in my set statement, when I say that I want to set the name of new client in this case is a reference expression. And a reference expression contains a reference by name. In this case, the name is new client, and we will need to associate this to this statement that introduced that variable so that we can figure out the entity that is used in this case. In this case, the reference expression should be resolved by using all the statements that can introduce variable declaration. In our simple language, it's just the create statement. So what we do here is to populate this reference by name with the name new client. I mean, after we run this part, now the referred field of the reference by name now points to the create statement, which is what we wanted. Now, in the set statement, we need to do something a bit more complicated. And if we go back to the example, here we are saying that we want to set the feature name of new client. But to figure out what is the definition of the feature name, we need to first find the type of the instance that we are using, because we could have possibly different features names called name in different entities. For example, we could have both a project and a client that introduce a feature called name. So what we need to do is to calculate the type of the field instance. And what we do in this case, when we have, in this case, our instance is new client, so it's a reference to the declaration new client. In this case, so, well, we check that we could resolve it properly, and then we return an entity reference type value. And how do we find the actual entity that we are referring? Just by navigating the references. So in my reference expression, I have the reference by name new client that points to the create statement. The create statement as a field entity, which is a reference by name that point to the definition of the entity. So I was able to navigate and find the entity. So once I have the entity, I can say to resolve my feature, just look for among the features of my entity. And so this should be solved. Another thing that we can see in the set statement in the check is the part where we check the type. In the case of the set statement, for example, we want to check that we are assigning a value that is compatible with the type of the feature. So for example, if my feature is a name, I cannot assign, I don't know, 3 as the value of the name. So we just calculate the type of the feature, the type of the value, and then we compare them. And if the value type cannot be assigned to the feature type, we will just add an issue. And I think that is the part of the interpreter that I can demonstrate today, because I want to leave some time for questions. But I want just to recap the main points. The main points are that we want to have a symbol resolution phase where we just navigate the reference by name and we drive the links, draw the links to the things that we refer to. Then we have these calculation types. Renee is asking if type checks are performed at runtime. In this case, we are able to perform the checks before actually executing the statements. In this particular case, there is little difference given that we then immediately after execute the statements. But for example, this is meaningful in case we wanted just to validate some script. So we will be able to have this, well, if you look at the code, here you see we have the result scripts and the check type script part. And at the end of this phase, in case we couldn't resolve some symbol, or in case we have types that were incompatible, the issue list will be populated, so we will add the error. So I could create a method, I don't know, check script that contains this part, but not this part. And for example, I could use that to show errors in the editor. So in this sense, there is benefit that we are not just checking things while execute statements, but also before, because we could potentially separate the two things. But yes, we can calculate types, and calculating types take advantage of the symbol resolution that we performed before. Sometimes there could be also an interdependency between symbol resolution and calculating type, but in this case, things were simpler. And then in most interpreters that are written, the core of the interpreter is basically an evaluate expression method and an execute statement method, which are typically a bunch of if. So if this expression is of this type, do this. If the statement is of this type, do that. So the design is really pretty simple. There are a few references. So, well, the Strumenta community. If you're here today, probably you know already about the Strumenta community, but in case someone is watching this video later, you can join the Strumenta community and we discuss these topics. Then you can watch the Antler mega tutorial. If you're really into Antler, you can consider our Antler video course. Then we have the the repository with Pylasu, where you can look at the code itself. And we are slowly building some documentation on StarLasu. If you are really into this topic, we have also some recording on some webinars we have given on building parser and transpilers. Yes, the code is available online, so you can find it here. Maybe I can also try to copy the link in the chat. Well, apparently I'm unable to. Later on, I will figure out how to do that. And so I guess it's time for questions, and I will stop the recording so we can ask all the shameful questions that we want. And if you're watching this recording, well, and you wanted to ask a question, it's time to join our virtual meetup. So let's see if I can stop the recording.